Good afternoon to everybody. Today we will discuss about inverse trigonometry functions. In the last class we have discussed about functions and the existence of inverse function. In the last class I have already told that if the function f is a bijective one, then only its inverse will exist. Suppose sin x is a trigonometry function. Its minimum value is -1, maximum value is 1. So sin is a real sine function. Its domain is real numbers and range is -1, 1. We have sin 30 degree half, sin 150 degree is also half. There are also other multiple of 30 degrees which having same value of half. Therefore, sin x is not a bijective function. So anyway, for the existence of this inverse function of sin x, we have sin is from -π/2 to +π/2 -1, 1. That implies sin inverse will be a function from -1 to 1 to -π/2 to +π/2. The values of sin inverse will lie in this interval -π/2 to +π/2. This is called principal value branch of sin inverse x, and the values which lies in this interval, the values lies in -π/2 to +π/2 are principal values of sin inverse x. So now I will write the inverse trigonometry functions. Here sin inverse x is an inverse trigonometry functions. An interesting question will be asked to you. Suppose sin inverse x and sin x to the power -1. What is the difference between these two quantities? Sin x to the power -1, that is 1 by sin x, that is cosec x. It is a real number. But about sin inverse x, it is an angle. So these two things are different. Sin x to the power -1 is cosec x, that is a real number, and sin inverse x is an angle. Now I will write the inverse trigonometry functions and their principal value branches. Principal value branches. Sin inverse x, that is closed interval -π/2 to +π/2. Cos inverse x 0 to pi. Tan inverse x, maximum value of tan x is infinity, minimum value is -infinity. So open interval -π/2 to +π/2. Then cosec inverse x -π/2 to close interval -π/2 to 0 union 0 to π/2. Similarly, sec inverse x 0 to π/2 union π/2 to pi. Half closed half open interval 0 to π/2 union half open half closed interval π/2 to pi. Lastly, cot inverse x is from 0 to pi. All these are principal value branches of the inverse trigonometry functions. Then we will go to properties of these inverse trigonometric functions. Number 1, theta equals to sine inverse sine theta. Proof. Let x equals to sine theta. That implies theta equals to sine inverse x. We can replace x again by sine theta. So theta equals to sine inverse sine theta. Similarly, we can write theta equals to cos inverse cos theta equal to tan inverse tan theta equals to sec inverse sec theta cosec inverse cosec theta and cot inverse cot theta, like this. Next property, x equals to sine inverse x. Let x equals to sine theta implies theta equals to sine inverse x. Now sine inverse x equals to sine theta, that equals to x. Similarly, we can write x equals to cos of cos inverse x, tan of tan inverse x, sec of sec inverse x, cosec of cosec inverse x, cot of cot inverse x, like this. Next we'll discuss about the point property where the relation between sine inverse x and cosec inverse x, relation between inverse trigonometric functions, sine inverse x equals to cosec inverse 1 by x. Let x equals to sine theta, that implies theta equals to sine inverse x. Now we can take 1 by x equals to 1 by sine theta, that is 1 by x equals to cosec theta, that implies cosec inverse 1 by x equals to theta equals to sine inverse x. So sine inverse x equals to cosec inverse 1 by x. Similarly, we can take other inverse trigonometric functions as cos inverse x equals to sec inverse 1 by x, tan inverse x equals to cot inverse 1 by x. Next property, sine inverse minus x equals to minus sine inverse x. Let us take, let x equals to sine theta, that implies theta equals to sine inverse x. Here in the LHS we have term inside the bracket is minus x, so here we can take minus x equals to minus sine theta, that is minus x equals to sine of minus theta, that implies sine inverse minus x equals to minus theta, that is minus sine inverse x. Similarly, we can take cosec inverse minus x equals to minus cosec inverse x, tan inverse minus x equals to minus tan inverse x. But the question comes, what about the cosine and sec functions? Next is cos inverse minus x equals to pi minus cos inverse x. Proof. Let x equals to cos theta implies theta equals to cos inverse x. Now minus x equal to minus cos theta, minus x equals to, we know that cos 180 minus theta is minus cos theta, so in place of minus cos theta we can replace cos pi minus theta, that is cos inverse minus x equals to pi minus theta. that implies cos inverse minus x equals to pi minus cos inverse x. Similarly, we can take sec inverse minus x equals to pi minus sec inverse x. Sec inverse minus x will pi minus sec inverse x. Cot inverse minus x equals to pi minus cot inverse x. Next property, sin inverse x plus cos inverse x equals to pi by 2. Either you can take actual sin theta or you can take actual cos theta. You can take according to your own choice. There will be no harm. Let x equals to sin theta implies theta equals to sin inverse x. Now x equals to sin theta, from your earlier classes or from school career you know that sin theta equals to cos 90 minus theta. That implies cos inverse x equals to 90 minus theta. That implies cos inverse x plus theta equals to pi by 2. That implies cos inverse x plus sin inverse x equals to pi by 2. Similarly, tan inverse x plus cot inverse x equal to pi by 2. For this, let x equal to tan theta. Either you can take actual tan theta or actual cot theta, there will be no harm. Implies theta equals to tan inverse x. Now, tan theta can be written as cot 90 minus theta. If you will take actual cot theta, in place of cot theta, you can take also tan 90 minus theta. That implies cot inverse x equals to 90 minus theta. That implies cot inverse x plus theta equals to pi by 2. Implies cot inverse x plus tan inverse x equals to pi by 2. Similarly, you can show that sec inverse x plus cosec inverse x equal to pi by 2 by using the formula sec 90 minus theta equals to cosec theta, or cosec 90 minus theta equals to sec theta. Next comes your next property, tan inverse x plus tan inverse y equal to tan inverse x plus y by 1 minus xy. Proof. Let x equal to tan alpha, y equal to tan beta. That implies alpha equals to tan inverse x, beta equals to tan inverse y. Let us start from RHS. Tan inverse x plus y by 1 minus xy equal to tan inverse. In place of x we can replace tan alpha plus tan beta whole divided by 1 minus tan alpha into tan beta. You know that tan a plus b equals to tan a plus tan b divided by 1 minus tan a into tan b. So this formula or this quantity will give rise to tan inverse tan alpha plus beta. As tan inverse tan theta equals to theta, that implies tan inverse tan alpha plus beta equals to alpha plus beta, that is tan inverse x plus tan inverse y, which is our LHS. So similarly, you can take tan inverse x minus tan inverse y equal to tan inverse x minus y by 1 plus xy. Just use the formula tan alpha minus tan beta divided by 1 plus tan alpha tan beta equals to tan alpha minus beta. Next property is sin inverse x plus sin inverse y equals to sin inverse x into root over of 1 minus y square plus y into root over of 1 minus x square. Proof. Let us take x equal to sin alpha, y equals to sin beta, that implies alpha equals to sin inverse x, beta equals to sin inverse y. So for convenience we will start from RHS. Sin inverse x into 1 minus y square plus y into 1 minus x square. In place of x you can put sin alpha, in place of y you can put sin beta, that is sin inverse sin alpha 1 minus sin square beta plus sin beta into root over 1 minus sin square alpha, that is sin inverse sin alpha. You know the formula 1 minus sin square beta equals to cos square beta. So taking the root over, that is cos beta, sin alpha cos beta. Similarly second term reduces to sin beta cos alpha. You have remembered the formula sin a plus b equals to sin a cos b plus cos a sin b. By the same rule, sin alpha cos beta plus sin beta into cos alpha will give you sin inverse sin alpha plus beta. So sin inverse sin alpha plus beta will be alpha plus beta, that is sin inverse x plus sin inverse y. Similarly, we can take sin inverse x minus sin inverse y equals to, just replace plus as minus x into 1 minus y square minus y into root over of 1 minus x square. Then we will move to next formula, that is cos inverse x plus cos inverse y. Cos inverse x plus cos inverse y equal to cos inverse xy minus 1 minus x square root over into 1 minus y square root over. For this, let us take x equals to cos alpha, y equals to cos beta, implies alpha equals to cos inverse x, beta equals to cos inverse y. Now we will move from RHS for our convenient RHS. Cos inverse, in place of x we can put cos alpha into cos beta minus 1 minus cos square alpha into 1 minus cos square beta, that is cos inverse cos alpha cos beta minus sin alpha into sin beta. You have remembered the formula 1 minus cos square alpha equals sin square alpha and 1 minus cos square beta equals to sin square beta, that is cos alpha cos beta minus sin alpha sin beta. This will give you rise a formula cos a plus b, that is cos inverse cos alpha plus beta, that is alpha plus beta, that is cos inverse x plus cos inverse y. So similarly we can take cos inverse x minus cos inverse y equals to cos inverse xy plus 1 minus x square root over into 1 minus y square root over. Next property is tan inverse x plus tan inverse y plus tan inverse z. 3 inverse trigonometric functions will be involved. Tan inverse x plus tan inverse y plus tan inverse z equal to tan inverse x plus y plus z minus xyz divided by 1 minus xy minus yz minus zx. Here 3 inverse trigonometric functions are involved: tan inverse x, tan inverse y and tan inverse z. Let x equal to tan alpha, y equals to tan beta, z equal to tan gamma. That implies alpha equals to tan inverse x, beta equals to tan inverse y, gamma equals to tan inverse z. Let us move from RHS. Tan inverse x plus y plus z minus xyz divided by 1 minus xy minus yz minus zx. So in place of x we can put tan alpha, in place of y tan beta, let us start from LHS. So, that is tan inverse x plus tan inverse y plus tan inverse z. Out of these three things you can take bracket of any two terms, there will be no harm. Tan inverse x plus tan inverse y will be tan inverse x plus y divided by 1 minus xy plus tan inverse z. Again we can put in the form tan inverse x plus tan inverse y, that is tan inverse x plus y by 1 minus xy plus z divided by 1 minus x plus y by 1 minus xy whole into z. In numerator we can take by taking the LCM as 1 minus xy x plus y plus z minus xyz. In denominator we can take 1 minus xy minus xz minus yz divided by 1 minus xy. So cancelling 1 minus xy, we have remaining terms as tan inverse x plus y plus z minus xyz divided by 1 minus xy minus yz minus zx. So in case of 3 trigonometric inverse functions, we can take the sum like this. But now the question comes whether sin inverse x plus sin inverse y plus sin inverse z. In case of 3 inverse sin inverse functions, whether we can apply the formula or not. In that case, we have to take a grouping of 2 elements and then solve. Next is sin inverse 2x minus 2x into root over of 1 minus x square equals to 2 sin inverse x. Let x equals to sin theta, implies theta equals to sin inverse x. So LHS will be sin inverse 2 sin theta into 1 minus sin square theta, that is sin inverse 2 sin theta into cos theta. We know the formula, 2 sin theta into cos theta is sin 2 theta, sin inverse sin 2 theta, which will give us 2 theta, that is 2 sin inverse x. Therefore 2 sin inverse x will equal to sin inverse 2x into 1 minus x square root over. Similarly 2 cos inverse x equals to cos inverse 2x square minus 1. For this, let us take x equals to cos theta. That implies theta equals to cos inverse x. Now from RHS, cos inverse 2 cos square theta minus 1. In place of x, we can put cos theta, that is 2 cos square theta minus 1. You have remembered the formula cos 2 theta as 2 cos square theta minus 1. That is cos inverse cos 2 theta, that is 2 theta equals to 2 cos inverse x. Next is prove that 2 tan inverse x equals to sin inverse 2x by 1 plus x square equal to cos inverse 1 minus x square by 1 plus x square equals to tan inverse 2x by 1 minus x square. For this, let us take x equal to tan theta. That implies theta equals to tan inverse x. Now, first term, that is 2 tan inverse x equals to 2 theta. Come to second term, that is sin inverse 2x by 1 plus x square. In place of x, let us replace tan theta, sin inverse 2 tan theta divided by 1 plus tan square theta. You might have remembered the formula sin 2 theta in the form of tan, that is 2 tan theta by 1 plus tan square theta, that is sin inverse sin 2 theta, that is 2 theta. Similarly, third term, cos inverse 1 minus x square by 1 plus x square, that is cos inverse 1 minus tan square theta divided by 1 plus tan square theta, that is cos inverse cos formula, cos 2 theta having the formula in place of tan, that is 1 minus tan square theta by 1 plus tan square theta, that is cos 2 theta. So here one thing you will remember, cos 2 theta has several formulas. In place of both cos and sin a, that is cos square a minus sin square a. In place of sin only, 1 minus 2 sin square a. In place of cos only, 2 cos square a minus 1. In terms of tan, 1 minus tan square by 1 plus tan square a. That is 2 theta. Similarly, fourth term, that is tan inverse 2 tan theta by 1 minus tan square theta. This quantitative term inside the bracket will be tan 2 theta, that is equal to 2 theta. So all the terms having the same value 2 theta, hence 2 tan inverse x equals to sin inverse 2x by 1 plus x square equals to cos inverse 1 minus x square by 1 plus x square equals to tan inverse 2x by 1 minus x square. Prove that tan inverse x plus cot inverse x plus 1 equals to tan inverse x square plus x plus 1. Your LHS involves two inverse trigonometric functions, tan inverse and cot inverse. We have the formula tan inverse x plus tan inverse y. Let us reduce this cot inverse into the form of tan inverse. Earlier I have told that tan inverse x equals to cot inverse 1 by x. So, tan inverse x plus cot inverse x plus 1 can be written as tan inverse x plus tan inverse reciprocal of this term, that is 1 by x plus 1. Now this is in the form of tan inverse x plus tan inverse y. Now we can apply our formula, that is tan inverse x plus 1 by x plus 1 whole divided by 1 minus x into 1 by x plus 1. That is tan inverse x square plus x plus 1 divided by x plus 1 whole divided by x plus 1 minus x divided by x plus 1. So cancelling x plus 1 and here also cancelling x. So tan inverse x square plus x plus 1, which is our RHS. Next question is, prove that tan inverse root over of xr by yz plus tan inverse yr by zx plus tan inverse root over of zr by xy equals to pi, subject to the condition if r equals to x plus y plus z. We have the formula tan inverse x plus tan inverse y plus tan inverse z equals to, I have told that, tan inverse x plus y plus z minus xyz whole divided by 1 minus xy minus yz minus zx, like this. So in place of x we can take the first term. So let us start from LHS, tan inverse root over of xr into yz, xr by yz plus root over of yr by zx plus root over of zr by xy minus product of these three terms xr by yz into root over of yr by zx into root over of zr by xy whole divided by 1 minus product of first two terms xr by yz into root over of yr by zx minus product of second and third root over of yr by zx into root over of zr by xy minus product of first and last root over of xr by yz into root over of zr by xy, like this. So that is tan inverse root over of xr by yz plus root over of yr by zx plus root over of zr by xy minus, this will be multiplying all these three quantities xyz r cube divided by y square z square x square whole divided by 1 minus root over of xr by yz into yr by zx minus root over of yr by zx into zr by xy minus xr by yz into root zr by xy. Root x into root y can be written as root over of xy. By that rule, I have multiplied all these quantities. So let us see which terms will be cancelled out. X will be cancelled, y will be cancelled, z will be cancelled. So numerator will be tan inverse xr by yz plus root over of yr by zx plus root over of zr by xy minus root over of r cube by xyz. In denominator 1 minus root over of, here we can cancel x, y, that is root over of r square by z square, r square by z square minus root over of r square by y cancel, z cancel by x square minus r square by y square. So on simplification, numerator will be as usual There will be no change. That is tan inverse root over of xr by yz plus root over of yr by zx plus root over of zr by xy minus root over of rq by xyz whole divided by 1 minus, removing all these root overs from last three terms in the denominator, that will be r by z minus r by x minus r by y. That can be written as tan inverse root over of xr by yz plus root over of yr by zx plus root over of zr by xy minus root over of rq by xyz whole divided by 1 minus r by xyz. Sorry. You can take a common of r, 1 by z plus 1 by x plus 1 by y, that is tan inverse root over of xr by yz plus root over of yr by zx plus root over of zr by xy minus root over rq by xyz whole divided by 1 minus r into xyz xy plus yz plus zx yz plus zr x minus xyz by r cube by xyz 1 minus over x can r square by z square r by z minus r by x that is tan inverse. You can take a common of r to the power half into root over of 1 by yz plus x by yz plus root over of y by zx plus root over of zr by z by xy minus r to the power 3 by 2 by root over of xyz whole divided by 1 minus r xy plus yz plus zx divided by xyz, like this. So from the numerator we can take a common of r to the power half tan inverse r to the power half. In these three terms we can take a LCM of root over of x, y, z. Here root over yz, root over zx and root over xy. So root over of x, y, z. So in first term we will have x, root x will be multiplied in the numerator plus y plus z minus r into r to the power half by root over of xyz whole divided by 1 minus r x plus y xy plus yz plus zx divided by xyz, like this. So that is tan inverse taking r to the power half common by root over xyz, we have x plus y plus z minus r whole divided by 1 minus r xy plus yz plus zx divided by xyz, like this. According to the question, r equals to x plus y plus z, that implies x plus y plus z minus r equals to 0. So now this numerator will reduces to 0. So that is tan inverse r to the power half root over of xyz into 0. I have written the reasoning here. Divide by 1 minus r xy plus yz plus zx whole divided by xyz. That is tan inverse 0. We know that tan pi is 0. So tan inverse 0 will be pi, which is equal to RHS. Next problem, find the value of cos, tan inverse, cot, cos inverse root 3 by 2. So for these type of problems, we will always start from the right hand side, that is cos, tan inverse, cot, cos inverse. You remember the trigonometric table, which value of cos is root 3 by 2? I hope it is cos 30 degree, or you can write pi by 6 also. Cos tan inverse cot 30 degree, that is cos tan inverse cot 30 degree. We know that tan 90 minus theta equals to cot theta. So cot 30 degree can be written as cos tan inverse tan 90 minus 30 degree. Or you can put the value of cot 30 also, no harm. Cos tan inverse tan will be 1, cot 90 minus 30 degree, that is cos 60 degree, that is cos 60 is half. So you can find the answer like this, or in place of cot 30 you just put the value, then find the value of tan inverse that quantity, then find cosine angle. Let us see another problem like this. Find the value of tan sine cos inverse root over of 2 by 3. Tan inverse sine cos inverse root over of 2 by 3. So let's start from the right hand side. For that we will have to make a substitution. Cos inverse root over 2 by 3, let it be theta. Theta alpha, you can take any variable, no harm. Cos inverse root over 2 by 3 equal to alpha. That implies root over 2 by 3 equals to cos alpha. From this we can, next term, if this quantity will be taken as alpha, then the question reduces to tan inverse sine alpha. From cos alpha we can find the value of sine alpha. Sine alpha is root over 1 minus cos square alpha, that is 1 minus 2 by 3, that is root over of 1 by 3 or 1 by root 3. So now this quantity equals to tan inverse sine 1 by root 3, because in cos inverse, in place of cos inverse root over 2 by 3 we have taken find the value of sine alpha. This quantity reduces to sine alpha, gives rise to sine 1 by root 3. First is tan inverse, second one is sine. So for the uniformity we have to make this sine function as tan. Let sine 1 by root 3 equals to theta. That implies tan inverse sine cos inverse cos inverse 2 by 3 sin alpha equals to 1 by root 3 tan sorry sin alpha equals to 1 by root 3. So this quantity will reduce to tan inverse 1 by root 3. I have done a mistake. Sin alpha equals to 1 by root 3. So in this whole term will give us sin alpha. So tan inverse 1 by root 3, that is 30 degree. Because your tan 30, that is sin 30 by cos 30. Sin 30 is 1 by 2 and cos 30 is root 3 by 2. So that will give you tan inverse 1 by root 3. That will give you 30 degree, or you can write in place of, in term of radians as pi by 6. Next, prove that sin inverse 1 by 3 plus sin inverse 1 by 3 root 11 plus sin inverse 3 by root 11 equal to pi by 2. Let us start from LHS. Sin inverse 1 by 3 plus sin inverse 1 by 3 root 11 plus sin inverse 3 by root 11. Let us make a group of these last two quantities. Now we can apply the formula sin inverse x plus sin inverse y. That is sin inverse 1 by 3 plus sin inverse, in place of x this and in place of y like this, x into root over of 1 minus x square, that is 9 by 11 minus y into 3 into root 11 into 1 minus 1 by 3 root 11 whole square. That is sin inverse 1 by 3 plus sin inverse 1 by 3 root 11. After simplifying this, this will be root 2 by root 11 minus 3 by root 11 into root over of, this will be whole square will be 1 minus 1 by 9 into 11, that is sin inverse 1 by 3 plus sin inverse 1 by or root 2 by 3 into 11 minus 3 by root 11 into 98 by 99, like this. That will be sin inverse 1 by 3 plus sin inverse root 2 by 33 minus 3 by root 11 into 7 root 2 divided by 3 into root 11. That is sin inverse 1 by 3 plus sin inverse root 2 by 33 minus 3 will be cancelled, 7 root 2 by 11, that is sin inverse plus sin inverse 1 by 3 plus sin inverse, taking 33 root as LCM root 2 multiplied by, that is sin inverse 1 by 3 plus sin inverse (22 root 2 by 3 into 49, 7 root 2 by 3 into root 11, 7 root 2 by 11. Then you can solve the problem by applying the formula sin inverse x plus sin inverse y. 1 by 3 1 minus 9 by 11 2 root 2 by root 11 plus 3 by root 11 1 minus 9 by 11 98 by 99 root 11 3 root 11 3 99 t. You can apply the formula sin inverse x plus sin inverse y equals to sin inverse x into 1 minus y square plus y into root over of 1 minus x square. In place of x, we will take 1 by 3, and in place of y, 22 root 2 by 33. Let us solve another problem. Prove that cot inverse AB plus 1 by A minus B plus cot inverse BC plus 1 by B minus C plus cot inverse CA plus 1 by C minus C equal to 0. So to solve this problem, let us reduce the quantities in LHS into tan inverse form. As tan inverse x equals to cot inverse 1 by x. So first term can be written as, first term of LHS can be written as tan inverse A minus B by 1 plus AB plus tan inverse B minus C by 1 plus BC plus tan inverse C minus A by 1 plus C. Remember the formula tan inverse x plus tan inverse y, tan inverse x minus tan inverse y equal to tan inverse x minus y 1 plus xy. So by that formula we can write the first quantity as tan inverse A minus tan inverse B plus tan inverse B minus tan inverse C plus tan inverse C minus tan inverse A. All the terms will be cancelled, that will give rise to 0. In another way you can solve like this. First apply your tan inverse x plus tan inverse A plus tan inverse Z formula. It will be lengthy one. Next is prove that sin inverse x by root over of 1 plus x square plus sin inverse 1 by root over 1 plus x square equal to pi by 2. Students, one important thing you have to remember, in place of 1 plus x square, you can take x equal to tan theta. In place of x square minus 1, you can take sec or cosec. In place of a square minus x square, you can take sec or cosec, or in place of x tan theta. And here the form is 1 plus x square. Let x equal to tan theta. That implies theta equals to tan inverse x. Now LHS equals to sin inverse tan theta by root over 1 plus tan square theta plus sin inverse 1 by root over 1 plus tan square theta. That is sin inverse tan theta. You remember the formula 1 plus tan square theta is sec square theta. So taking root over, that is sec theta plus sin inverse 1 by sec theta. That is sin inverse tan theta by sec theta after converting it into sin and cos form. That will be sin theta plus sin inverse cos theta. Sin inverse sin theta is theta plus sin inverse. In place of cos theta we can take sin 90 minus theta. Now sin inverse sin will be 1, that is theta plus pi by 2 minus theta, that equals to pi by 2.